We are lecturing now for 16B. You did some work with redox reactions, reduction, and oxidation in 16A where you guys did the posters last week. But we are now going to do a quick little review of that and then go into more of the application of these things. We're taking electrons from those that have and giving them to those without. It's kind of like a Robin Hood of electrons is what a redox reaction is. Called redox because it's reducing part of it and oxidizing part of it. And so they're very important reactions for batteries and for a lot of electrochemistry. Okay? So I'm going to give you actually just a second to write that down before I start talking because there's a lot of words. So letter A there on the notes, this is a review of 16A. So this is, you've already had this, but I just wanted to make sure that I've talked about it as well. In a reaction, if we care about where the electrons go, then you can identify oxidation numbers for different elements in the reaction, and you find the oxidation of it before the reaction happens, and you find the oxidation number of it after the reaction happens. And you can see if something has been oxidized or reduced. So just some terminology review. Any element that loses an electron in a reaction has been oxidized. And we call it that because oxygen is usually the thing that takes the electrons away from it. And so reacting something with oxygen was the first time that this was studied. And so the name oxidized came to be used for anything that has lost electrons. But more than oxygen takes electrons. And so you don't have to have oxygen in a reaction for something to have been oxidized. It's just that oxygen is the first time that that showed up as people were discovering this in chemistry. So oxidation means I lost electrons. And then the element that stole those electrons from the thing that got oxidized, we call it oxidizing agent. It is what snuck in and grabbed the electrons. Okay, so oxygen again was the first oxidizing agent that was discovered, but lots of elements grab electrons. Any of the halogens would be very happy to grab an electron and therefore be an oxidizing agent. And so something that steals electrons is an oxidizing agent. The thing that has been oxidized is the thing that's been oxidized is gave up electrons. Any element which gains electrons in a reaction has been reduced. So Abraham asked last week, how come it got electrons and then we say that it's been reduced? Well, an oxidation number is the number of electrons that it has to gain in order to go back to being neutral. And that number goes down as you lose these electrons. And so it's the oxidation number that goes down, which is why we say that it's been reduced. Okay. So the oxidation number goes down, which is why we say it's been reduced. And the thing that gave it the electrons is the reducing agent. So a reducing agent gives electrons to something which reduces it. An oxidizing agent takes electrons from something which oxidizes it. And then those usually happen at the same time. So in a reaction where electrons travel from one thing to another, an oxidizing agent oxidizes something and is itself reduced because it took electrons from something, and so that thing has been oxidized, and now it has the electrons, so it has been reduced. And on the other side, that thing lost electrons, so it has been oxidized, but it gave its electrons over there, so it is the reducing agent, but it was oxidized. Okay? So in a redox reaction, an oxidizing agent is reduced, and a reducing agent is oxidized. And that is a redox reaction. That is review from 16A, and now we're going to look at how this plays out. There's a quick little acronym that helps you remember this. Leo the lion says grr. Leo, grr. Leo, loss of electrons is oxidation. Gain of electrons is reduction. So That's kind of an easy way to remember which one is oxidation, which one is reduction. If you lose the electron, you've been oxidized. If you gain the electron, you've been reduced. Leo the Lion says error. There you go. And again, reduction and oxidation usually happen in the same reaction, or not usually, they do happen in the same reaction. So if element A has 2 electrons, and then the reaction happens, and those 2 electrons wind up with element B. Now, element A has been oxidized because it lost these 2 electrons that it used to have. Element B has been reduced because it gained 2 electrons. But notice that B is the oxidizing agent because it's what oxidized A. So the oxidizing agent is reduced, and the reducing agent is oxidized. That's what happens in a redox reaction. Okay? Take a second, write this down. Okay, before we analyze a redox reaction, we need to identify the oxidation numbers for every atom in the reaction. And so these red numbers that I've written above here, these are the oxidation numbers. And the oxidation numbers can be found by looking at the atom or the molecule and saying, if I were to just cut these atoms apart out of the molecule and make any shared electrons go with the more electronegative atom, what would the charge on that be? There are more complicated rules for finding the oxidation number, but that's kind of the kernel of it. Take an atom, look at it as it's bound to the rest of the atoms in the molecule, and say, if I were to just pull you out of the molecule and make the more electronegative atom in a bond keep the pair of electrons, what would the charge be? And so that gives you the oxidation number. You can look at the rules in 16A on how to determine oxidation number, and there's several rules that go with it. But the idea there is just what's the charge within that molecule. So if you look here, potassium and chlorine are being bound to oxygen. Now, oxygen is more electronegative than either chlorine or potassium. So when it's sharing electrons with these guys, it wins all the time. And so there are 3 of these oxygens, and they're going to win in the electron tug of war with potassium and with chlorine. And they're going to wind up keeping the 2 electrons out of the pair that it was sharing with those things. So each oxygen becomes -2. That would be its charge. If you were to like rip it violently out of the molecule and look at it, it would be -2. And then there's 1 chlorine and 1 potassium here in the molecule. Part of the rules of oxygen or of oxidation rules is that oxygen is always -2 in a molecule, so that's why we're there with it. And the group 1 elements are always +1. So potassium is a group 1 element, it's always +1. So you look at this and you say, okay, well, what does that mean chlorine has to be? Chlorine has to balance the rest of it. It has to make it all equal 0. So if there are 3 oxygens that are each -2, that's a total of -6. And the potassium is only accounting for +1. Well, chlorine has to make up the difference. So what did chlorine do to make the molecule net 0? +1 minus 6, we've got to have +5 to balance this whole thing and make it add up to 0. So chlorine has an oxidation state of +5. Potassium's +1, oxygen is -2. Potassium +1 again, chlorine -1. Now, first group elements are always +1. So if you have a +1 and something that balanced to 0, well then that's -1. +1 minus 1 equals 0. So here chlorine went from +5 to -1. And now oxygen is by itself. And one of the other rules in 16A that you learned is that if you only have an element by itself or bound to another atom of the same element, then it's 0. So oxygen by itself is 0. So oxygen went from -2 to 0. Chlorine went from +5 to -1. So we would say that chlorine is reduced. Its oxidation number went down. Its oxidation number got smaller. So chlorine was reduced, and oxygen is oxidized, as it went from -2 to 0. Its oxidation number went up. Anytime oxidation numbers go up, it's been oxidized. Anytime oxidation number goes down, it's been reduced. So this is a redox reaction, okay? And when we balance these things, we have to balance them not only thinking about 2 potassiums, 2 potassiums, 2 chlorines, 2 chlorines, 6 oxygens, 6 oxygens, but we also have to look at it and see that the electrons are balanced. Here I have the oxidation numbers that total to 0, and here I should have oxidation numbers that total to 0. And so we have to balance electrons as well as balancing the individual atoms. Okay? And this was, again, gone over in 16A. I'm just making sure that you have it in a couple of different sources. Any questions about what I just did? Okay. So here we have a stick of zinc in a copper solution, cupric sulfate solution. And the copper is going to wind up coming out of solution and sticking to the zinc. It's kind of interesting. And you'll wind up with clumpy copper on the zinc, and then the zinc will be going into solution. So the example here, zinc as a solid and copper as an ion attached to the sulfate. And here then we have zinc as an ion and copper as a solid. Well, anytime you have something by itself, its oxidation state is 0. So the zinc by itself has an oxidation state of 0, and the zinc as an ion has an oxidation state of +2. So its oxidation number went up, which means that the zinc is oxidized. And here the copper has an oxidation state of +2, and here copper by itself has an oxidation state of 0. So from +2 to 0, the oxidation number went down. So copper was reduced. Okay. So you can it's sometimes helpful to write these things as half reactions and just show that the zinc went from a solid by itself to an ion in solution. And so we have electrons that were taken away, and that shows very clearly that it's been oxidized. And here we have 2 electrons being added to copper to make it just itself, and so that shows very clearly that it's been reduced. So sometimes that's helpful to write just a half reaction, and then it helps you see where the electrons are going. This is just another example. Silver nitrate in solution, and then you add a copper strip to that, and the copper is going to go into solution, and the silver is going to clump up on the strip, and you'll wind up with silver coming out of solution and copper going into solution. And again, the silver in solution is an ion. The silver clumped up out of solution is a solid, so it's by itself. And so its oxidation number went from positive something to 0. Its oxidation number went down, it's reduced. And the copper by itself had an oxidation number of 0. It became an ion, it became plus something, it went up, so it was oxidized. Okay? We're going to apply this to batteries now. Take a moment right back. So redox reactions are used in lots and lots and lots of places, but the one that is most common and that you will run into the most in your life as a consumer of technology is a battery. A battery is a redox reaction. Every battery is a redox reaction. And so we're going to look at electrochemical cells, which are redox reactions going on, and we're getting electricity from those. Anytime you have something, a solute, dissolved in water that dissociates, and so it turns into ions. Those ions allow electricity to flow through the solution, and we call the thing that was dissolved an electrolyte. Okay, so we use electrolytes in biology as well. the reason that if you're working out a lot, you want to drink something like Gatorade as opposed to just always straight water is you're sweating out salts, and those salts are necessary for your body's chemistry. And if you are replacing salty water in sweat with only pure water, then you're going to eventually run out of electrolytes, and that can cause serious problems to your body. So we use electrolytes in biology as well. Here we're using them for their electrochemical potentials, and we're talking about that in batteries, but it's the same exact stuff. Your body has electrochemistry as well and needs electrolytes. Batteries have electrochemistry and need electrolytes. Electrolyte is something dissolved in water that allows electricity to flow, allows a current to flow. And when we take an electrolyte and we put two different metals in the electrolyte, we get an electrochemical cell. And it doesn't matter what those two different metals are as long as they're different. You can't put two pieces of copper in a strawberry and get a battery out of it. But if you have a piece of copper and a piece of iron, you'll get a battery out. Some metals work better than others. You'll play with this in a lab where you'll be able to say that these two metals, when you put them in a piece of fruit, get a higher voltaic potential than these two different metals that you put in the fruit. So as long as you have two different metals bathed in an electrolyte, then it works, and you'll get some current from it. But some metals work better than others. Okay, so an electrochemical cell, two dissimilar metals bathed in an electrolyte. There are two reasons you would do this. You could do this because there's a non-spontaneous reaction that you want to make happen. And so you're going to set this reaction up, and then you're going to hit it with electricity and force the reaction to happen. If you're doing that, then we call it an electrolytic cell. And we'll do that in a lab as well next week. In an electrolytic cell, you have something that could theoretically happen, but it goes against the Gibbs free energy for that reaction. And so it won't happen on its own. But if you give it energy by adding electricity to the reaction, then all of a sudden a reaction that won't happen on its own happens. So we'll do that in a lab next week. The thing we're going to do this week is the voltaic cell, where you set up a spontaneous reaction, a reaction that will happen on its own. And you catch the electrons that are going from one side to the other, and you make those electrons do work for you. You're getting electricity out of it. So as one element that has electrons is being oxidized, and those electrons are flowing over to another element that is being reduced, you just use that electron flow and make it do work for you. So in a battery, something is being oxidized, something is being reduced, and the electrons don't get to flow straight across. The electrons have to go through your laptop first. And so your laptop uses that flow of electrons to do work with it, and then the battery is still just an electrochemical reaction going on, but you're kind of pirating those electrons as they flow from one element to the other and using them for something. Okay, that's called a voltaic cell because we get volts of electricity out of it, and because it was discovered by a guy whose last name was Volta. So a voltaic cell. Kind of funny, does anybody know the story of how we got the first voltaic cell? Anybody hear that? It's a guy who was dissecting a frog. And so the frog's body chemistry was the electrolyte, right? The frog juice. And he had a scalpel of one different metal, and he had a probe of a different metal. So I don't know what they were. Let's say his scalpel was steel, and his probe was copper. And he was dissecting the frog, and the current being produced was too weak for him, as long as he held them in different hands, to feel the current. But at one moment, he held them both in one hand, and they were both touching the frog, and he got shocked. He's like, what in the world? What was that? And that gave him the impetus to figure out what's going on there. And the first voltaic cell was two different dissection tool metals in the frog. And we're going to be doing that with fruit, not with dead frogs. But it's the same idea. So this is an electrolyte solution, and we're just showing that things have to dissociate in order to conduct electricity. Sulfuric acid dissociates in water, and so electricity can flow between these two electrodes and the light bulb lights up. But sugar does not dissociate, so you can have sugar water, but it doesn't conduct electricity. So in order for an electrolyte to work, it has to dissociate in solution and become ions. Sugar doesn't do that. Okay, I think this is your last slide. Take a second, write that down, and we'll start talking about it. So electrolytic cells, remember, take a non-spontaneous reaction, add electricity to it, and force that reaction to happen. We use this for getting metals out of their natural ores. A lot of times metals bound with other things that they're hooked up with in the earth are very stable, and it's very hard to get an ore to turn into a pure metal. Certain metals come out of their ores easily, which is why low-tech people thousands of years ago were able to have things like lead and copper and those sorts of metals, because you can get them out of their ore easily. All you got to do is heat it up and melt it or something like that. But other ores, like aluminum, are very hard to separate out of their natural compounds into the pure metal. And until we discovered about electrolytic cells, and until we figured out how to make that happen with electrochemistry, aluminum was really expensive because it's very hard to get aluminum, pure metal, out of the ore. Once we figured out how to do this, though, the price of aluminum dropped, and aluminum used to be, something that was a valuable commodity, like gold or silver, because it was so hard to purify. But now aluminum is so cheap that you wrap your hot dog in it and then throw it away. So the difference is the technology to get it out of its natural ore. Electroplating is another way that we use electrolytic cells. You have some cheap metal that nobody wants to look at, and you want this to turn into a piece of jewelry. Well, nobody's going to be excited about your nickel pendant. They're like, oh, and then your skin turns green underneath it, right? But if you take your nickel pendant and then put it in a solution of silver and give it a little bit of electricity for a while, silver clings to the nickel, and now you have a silver pendant that doesn't turn your skin green. And everybody's like, oh, how pretty. But the only silver is the very thin layer on the outside, and most of it is cheap nickel underneath it. So electroplating is another thing that we do with that. Frequently done in coins and frequently done with jewelry. Okay, and then voltaic cells we use for batteries. We have one metal that is being oxidized, and we call that the anode, and we have one metal that is being reduced, and we call that the cathode. And we catch the electrons as they flow from one to the other, and we make it do some work. That's electricity. Modern batteries do not have the two electrodes in the same bath of electrolyte because we're able to slow down the reaction even more and catch all of the electrons if we keep them in separate electrolytes. But the electrolytes have to complete the circuit. We've got to still allow them to communicate their ions, and so they make this thing called a salt bridge that allows ions to flow through the salt bridge without allowing the actual liquids to mix. And so a salt bridge is just a way of controlling the electron flow even more and getting all of the possible benefit out of the electrochemical reaction that's happening. So let me show you some pictures here. This is a simple electroplating apparatus. We have a bar of silver, and we have aqueous silver nitrate, so there's silver ions in the solution. And then we have some iron spoon. Well, nobody wants to eat an iron spoon. We want a silver spoon. So we dip the iron spoon in this bath that has dissolved silver in it. We pass an electrical current through it, and silver ions leave the bar of silver and go into solution. And then the silver ions in solution jump onto the iron spoon and stick there. And we wind up with an iron spoon that has a silver coating on it. And then that looks pretty, and people want silver spoons. Okay, this is the reduction of aluminum to get aluminum out of its ore, and we have a molten solution of aluminum, and then we heat it up to stupid amounts of temperature, and we pass an electric current through it, and we wind up getting all the weird stuff that's stuck to the aluminum to cling to one of the anodes, and the molten aluminum by itself drifts down to the bottom. So that's how they get aluminum out of ores now. And then this is a battery, and this is the stuff we'll be playing with mostly, where you have a cathode and an anode, and you have an electrolyte, and then this salt bridge that allows the ions to pass, but doesn't mix the liquids. And as the electrons move from the copper to the silver, we're able to catch them and use them for electricity. Okay, and then they eventually do flow back into the cathode, and we have a battery that works. Okay, so a lot of times the name of a battery will tell you what is going on in there, what kind of chemical reaction is going on in there. If you've heard of like lithium-ion batteries, well, lithium is serving as the source of the anode, as the source of the electrons, and then there's other ions in there that are reacting with it. We're using the electrons from the reaction. Okay, so or a lead acid, the lead is the anode. So that is a battery. Any questions? We will play with this with a lot of labs this week, so it should clarify if you have any. Okay, that is it. Please get